This is Gaydon, Austin Rover's proving ground. It's here that the company's new cars are put through their paces before being launched to the public. The Rover 800 was the latest product to emerge from the rigorous test routines that Gaydon has to offer. Every component and system thoroughly checked. Suspension, gearboxes, brakes, body, and above all, the engines. This is where the 2.5-litre V6 engine, which powers the 825i and Sterling models, was tested to assess durability, economy, and power. But as any engineer here at Gaydon will tell you, the V6 engine has a superb performance all round. Now, in this program, we're going to be looking at the controlling factor behind the V6 engine. How can one engine deliver all the energy and pulling power of 170 brake horsepower and at the same time offer tremendous reliability and refinement? Well, the answer is PGM-FI, the Programmed Fuel Injection System. Everything from air and fuel flow to ignition control, engine speed and position is regulated and constantly monitored through the PGM-FI's electronic control unit. Nothing is left to chance. Using information taken from sensors all around the engine, the ECU can formulate the exact fuel requirements for any given road condition, and it can control the flow of air into the engine. The net result is that whether the engine is warm or cold, accelerating or decelerating, the car will always run smoothly. The ECU is the brain behind this system, receiving information and acting on it with split-second timing. But why is this system so good? Well, the heart of a modern engine is its engine management system. And this one is just a little bit special. Now, there are many different fuel injection systems, and they all operate in different ways. But in principle, the best time to inject fuel is on the piston intake stroke. And that's what the PGM-FI system does. It's a sequential, multi-point injection system. Now, this is where the importance of split-second timing really comes in, because for the system to be effective, the ECU must know accurately when each piston reaches its top dead center position. And that information is provided by this, the crank angle sensor behind the front camshaft gear. These are magnetic pickups. When the camshaft gear rotates, poles in its circumference pass the pickups, inducing a small current. And this current forms the signal sent to the ECU. Now, the single pole on the outer circumference is used to detect top dead center position of number 1 cylinder. This information means that the ECU always knows when to start the injection sequence. The 6 inner poles relate to the top dead center positions of all 6 cylinders, and they determine when fuel should be injected into each one. So, that's how the ECU calculates the position of the engine at any given time and how it controls both the sequence and time at which fuel is injected. At this stage, I'm going to follow the first rule in the Book of Mechanics' Good Garage Practice and fit the wing cover. But you know, it's not just the timing of fuel injection that this system can control. It also works out the amount of fuel to inject and constantly alters injector duration. For this, the ECU has to determine both the speed of the engine and the loads placed on it. The speed signal is again received from the crank angle sensor. The information from the 6 inner poles on the camshaft gear provides the speed signal. The load signal is provided by the manifold absolute pressure sensor, or MAP sensor for short. It's inside this control box on the bulkhead, just there. And it's connected by vacuum pipe number 3 to the manifold side of the throttle body. The greater the load on the engine, the higher the manifold pressure. So, the speed and load signals provide the basic information for fuel delivery. But on their own, they're not accurate enough. To cater for all driving conditions, there are 4 other sensors. The coolant temperature sensor, which signals the ECU to extend injector duration when the engine's cold. An intake air temperature sensor, which also signals the ECU to modify injector duration when necessary. A throttle angle sensor monitors throttle position and rate of movement. It tells the ECU when more or less fuel is needed. And lastly, an atmospheric pressure sensor that's bolted to the side of the ECU. Now this allows injector duration to be altered according to changes in altitude. So, if you're driving in the Alps or even around the Dead Sea, you'll be okay. This system's got it all worked out. All the driver has to do is sit back and enjoy the drive. But as they say, there is more. We know that accurate timing of fuel injection and the quantity of fuel injected are important. But the engine must have a controlled supply of air to obtain the optimum air-fuel ratio for the engine to run smoothly. That's the job of the air intake system, to control the flow of air into the engine. Filtered air passes along this pipe into the throttle body here. Now, I want to show you a separate throttle body assembly. There are two throttle valves, a primary and a secondary. Primary valve is operated directly by a throttle cable, and I'm going to use my thumb as a substitute. Once it reaches a preset opening there, the secondary valve opens by means of a connecting linkage, like that. Now, a damper is fitted here on the primary throttle valve to smooth the throttle return, preventing driveline snatch during deceleration. Right, let's take a look at the idling speed controls. Now, fast idle speed is controlled by the fast idle valve here. It increases the idle speed during the initial warm-up by providing the engine with more air. So how does it do this? Well, it's really quite simple. There's a wax capsule immersed in engine coolant. This controls the opening and closing of the valve. When the engine's cold, the capsule contracts, opening the valve. Air is directed around the throttle disc, increasing idle speed. As the engine warms up, the wax capsule expands, the fast idle valve closes, and the engine gradually returns to normal idle speed. But, and it's a small point to note, if fast idle continues after the engine's warmed up, or it's reduced during warm-up, then the valve could be faulty. Okay, that's how fast idle's controlled, straightforward enough. But what about controlling normal idle speed? Once the engine's reached normal operating temperature, idle speed is controlled by the electronic idle control valve, or EICV for short. It's a solenoid-operated air valve with a water jacket to prevent icing in cold weather. The ECU changes the valve's position, varying the amount of air bypassing the throttle disc, so it compensates for fluctuations in idle speed and prevents stalling. Well, now, if you need to set the EICV, there's an adjusting screw here on the throttle body. So just one small valve, by opening the right amount at the right time, plays a major role in controlling the flow of air to ensure the engine idles correctly. Now, the last thing we're going to look at on the air intake is the exhaust gas recirculation system. This device helps the engine in two ways. Recirculation not only reduces poisonous exhaust fumes, but it creates turbulence in the inlet manifold, improving combustion. The exhaust gas recirculation system has three main components: an EGR valve here on the front cylinder head, a constant vacuum control valve here, and a control solenoid here, both in the control box on the bulkhead. The ECU determines when exhaust recirculation is required and energizes the solenoid. Manifold vacuum is then directed through the constant vacuum control valve to lift the EGR valve. This allows exhaust gases from number 6 cylinder to enter the inlet manifold. The constant vacuum control valve, as its name suggests, controls the amount of vacuum applied to the EGR valve diaphragm. This sensor tells the ECU the position of the EGR valve. The ECU will then set the valve lift to its ideal position for the prevailing conditions. Right, that covers the PGM-FI air intake system. We've seen the operation of the fast idle valve, the electronic idle control valve, and the exhaust gas recirculation system. They all play an important part in keeping the engine running smoothly. And smooth running and high performance is a hallmark of the V6 engine. Driving around the test track here at Gaydon makes you appreciate just how much all this technology is actually helping the engine, delivering power when it's needed and where it's needed. Of course, driving in the United Kingdom is generally under favourable conditions, give or take the odd torrential downpour. But today's engine needs to perform well under any conditions, in the Arctic or in the Sahara. This climatic chamber can test engine performance in temperatures from -40 to +55 degrees centigrade, together with wind speeds of up to 100 miles an hour. Solar simulation and controlled humidity complete the picture to test engines to their limits. But any car needs fuel to keep going, and irrespective of climatic conditions, you have to have a consistent fuel supply for the Rover to run smoothly and efficiently. In other words, you need a good fuel system. PGM FI provides the answer. The PGM FI fuel system is a full-flow, high-pressure recirculating system. Fuel's pressurized by an electric pump in the tank, and it passes through this filter before going on to the fuel rails here and here. Now, fuel pressure is around 2.7 bar, but it can stay this high even several hours after the engine's been switched off. So it's important to remember, always relieve the pressure before disconnecting the fuel lines. Fuel pressure is controlled by a regulator here on the fuel rail. It acts as a spring-loaded restriction in the fuel line before the petrol returns to the tank. The regulator has two chambers, here and here, separated by a diaphragm which has a spring acting on it. When the fuel pressure rises above 2.85 bar, it overcomes the spring pressure, raising the diaphragm. Excess fuel passes back to the tank through the return line. During cruise, idle and overrun conditions, when manifold pressure is low, vacuum around the injector nozzle has the effect of pulling extra fuel from the injector, which would cause an overrich mixture. To avoid this, manifold vacuums fed to the upper chamber of the regulator, lowering fuel pressure. And this means, regardless of manifold pressure, the ECU knows that a particular injector duration will always give the same fuel delivery. Now, with high temperatures under the bonnet, one of the problems is that fuel can vaporize in the rails, and this can lead to poor hot starting. To overcome this, the ECU, influenced by the coolant temperature sensor and the intake air temperature sensor, opens a valve in the control box, allowing atmospheric pressure to enter the upper chamber of the regulator. So, more fuel pressure is needed to lift the diaphragm, and this increased pressure improves hot starting. Now, inside the car, there's another vital component of this system. There's a relay under the dash. It's actually just behind the fuse box. Now, this is the main relay, which controls the feeds to the ECU and the injectors. And when the ignition's switched on, this activates the fuel pump for a couple of seconds, just enough to pressurize the system before cranking. When the engine's cranking or running, the relay allows the fuel pump to run continuously. Well, finally in the fuel system, let's take a look at the fuel injectors themselves. They're solenoid operated with a pintle tip to atomize the fuel. If you need to remove an injector, I've taken one out here, always renew the seals there and there and the cushion ring. The injectors are fed via this resistor pack, and this allows the use of smaller injector coils, giving a faster injector response time. And one other point to remember, don't pull on the harness connector before you unfasten the clip here, or you could damage the connector. So, the injectors deliver the right amount of fuel at the right time, but the mixture's got to be ignited at the right time for the system to work efficiently. Ignition timing control is another important function of the ECU. It controls a vacuum advance system which works along with a conventional centrifugal ignition advance. The ignition control system has two vacuum advanced diaphragms, and I've got a cutaway one here to show you. One there and one there. They're operated by two ignition control solenoid valves and a vacuum reservoir and check valve. Within this system, the ECU can implement 4 different levels of ignition advance to suit all operating conditions. So, that's ignition advance. But what else does this ECU do? Well, it even maintains a stable idle speed when air conditioning or power steering loads are applied to the engine. All these varied functions of the ECU make it the most powerful controlling force within the system. But it's got one more facility which sets it apart from other control units, that of self-diagnosis. This really cuts down the time you have to spend on fault diagnosis. Now, the ECU can, for example, tell when the EICV needs adjusting. Now, obviously, to adjust that, you would have to have the engine running, and this one quite clearly has been disconnected. But if you were doing this for real, and if the EICV was out of adjustment, then a yellow LED would be lit up behind this window. If the LED was flashing, then you would need to turn the adjusting screw on the throttle body clockwise. If the LED was constantly lit, then you would turn this adjusting screw anti-clockwise, and you would turn in small increments, waiting for the reaction until the light went out. If you have had to make an adjustment to the EICV, it's just possible that the CO content will have changed. So it's most important to check the idle CO content with an exhaust gas analyzer. And if necessary, adjust the mixture according to the instructions. Now, the adjusting screw is there in the control box on the bulkhead. It has to be adjusted by very small increments, and between adjustments, wait for the meter to settle. Now, in addition to the yellow LED, there's a red one beside it. And this gives up to 14 different fault diagnosis trails. If there is a fault in the system, the LED blinks a certain number of times, pauses for a couple of seconds, repeats the sequence. And by the way, you'll find the list of fault codes in the fault diagnosis manual. If the ignition is switched off, the fault is held in the memory of the ECU. Once you've rectified a fault, always either disconnect the battery or remove the 10 amp alternator fuse and keep it out for at least 10 seconds to clear the memory. So that's the theory, but fault diagnosis is all about putting the theory to the test. So how does it work in practice? Well, to warn the driver that there is a fault somewhere on the system, there is a light which illuminates on the instrument panel when the LED is flashing here. Now, I must tell you, we have doctored this car to introduce a fault into the system. Let's say that the owner has come in and he's complaining of flat spots during acceleration. First thing to do is to confirm that there is a problem by turning on the ignition, and there we are, the PGM FI warning light is on. So let's check the ECU, and as you can see there, the red LED is flashing. Now, if that LED was constantly lit, it would mean that there was a fault in the ECU itself, in which case a backup circuit would come in to control the system. The engine would continue to run, but at reduced performance. Now, as it is, this LED is flashing seven times. There is a list of fault codes in the fault diagnosis manual, and if I go down, 7 blinks means that the problem is in the throttle angle sensor circuit. Well, now, check the obvious first. Make sure that the harness connection is okay, which is down under here, which it seems to be. Now, apart from a damaged or disconnected connector, the most likely fault is maladjustment. To check that, I'm going to have to connect either PGM FI Fast Check or Cobest into the system. Now, to connect Fast Check, disconnect the ECU and plug the Fast Check into its harness. Switch on the ignition and just check that the power and ignition LEDs are lit. And then it's a matter of going through the tests by pressing the proceed button. And the test for the throttle angle sensor is number 22. 19, 20, 21, 22, and there we are. The fail LED is illuminated. Now that means either that the sensor is faulty or that it needs adjusting. We'll assume that it needs adjusting. Make sure before you start to adjust that the throttle is in the fully closed position. Release the locking screws. That is tight as usual. You're going to have to take the one below the sensor using a spanner. Right. Now, turn the sensor either way until you find a point midway between when the pass light comes on and goes off, which is there. Lock up the sensor into that position again. And it's as simple as that. Now, all the test and diagnosis information is contained in the fast check instructions. So as you go through the tests, do follow these very closely. With Cobest, fault finding is even easier because Cobest tells you exactly what to do. Right. It plugs into the system in exactly the same way as fast check. There's one single connector box, but the principle's the same. It plugs into the ECU harness. There. It starts with an automatic test sequence which checks the system as a whole. And during that sequence, it asks for the engine to be cranked so that certain parts of the system can be tested dynamically. Now, with fast check, the position of the throttle angle sensor was tested only when the throttle was at rest. With Cobest, it checks the whole range of the throttle angle sensor by asking the operator to depress the throttle slowly. Now, to save time, we've gone through a whole component test sequence on this car, which has had exactly the same fault doctored into it as the previous car. Well, as you can see, all the tests have been passed except one, and that's the throttle potentiometer. So let's continue. This should take us into the corrective service sequence. Switch off ignition. Keep going. Ignition off, which it is. Ensure that the throttle is fully closed, which it is. Now I can loosen off the locking screws in exactly the same way as I did before. Now, what I need to do is to get the setting between these limits of 0.4 and 0.6 volts. In other words, I need to aim for about 0.5. We're obviously in a fail situation at the moment, so there we are, 0.5, and I can now start to lock up again. The great thing about fast check or Cobest on a comprehensive system like this is that you can trace faults in minutes rather than in hours. Now, because the ECU can hold a record of faults in its memory, it is worth checking for intermittent faults. For example, if you've been through and checked everything and there are no faults appearing on Cobest, but you've still got an LED flashing, you could have had an intermittent fault in the form of, say, a damaged or loose connector. Check for those before you erase the memory of the ECU. Now let me give you a few tips on day-to-day working with the PGM-FI. First of all, if the yellow LED is flashing or constantly lit during the first 1,000 miles, then ignore it. The EICV will compensate for high friction in the engine during the initial running-in period by opening further than usual. If the fault's still there at the 1,000-mile after-sales service, that's the time to make the adjustment. And by the way, if you are adjusting the EICV, the engine must have reached normal operating temperatures before you do so. Let's assume that your customer comes in complaining of stalling or uneven running at low speeds. One possibility is that you've got a cracked or disconnected hose between the manifold absolute pressure sensor, which is here, and the air intake manifold. So check hose number 3 very carefully. If that hose is damaged, the ECU will register high manifold pressures, and that will cause an overrich mixture in cruise, idle, or overrun conditions. One other reason for stalling or uneven running is if the EGR system is constantly operating. So check for a kinked EGR hose. That, by the way, is hose number 10. It runs right the way down here, and it runs right along here, so check it all the way along its length. And also, make sure that the EGR control solenoid isn't seized. If the idle speed's high, then check the red LED, because a fault shown there will very often be accompanied by a high idle speed. If you get a constantly high idle speed, then it may be that the fast idle valve is faulty, and that is easy enough to check. First of all, remove the valve cover. Right, can you start the engine? Thank you. Now, with the engine cold, you should be able to feel a flow of air through the valve. If you can't, the valve's faulty, reject it. When the engine's reached normal operating temperature, you shouldn't be able to feel that flow any longer. If you can, before you condemn the valve, just make sure that the coolant pipes to the valve aren't blocked. If you have an automatic in, and the complaint is of poor fuel consumption, then the problem may lie in a faulty torque converter lockup solenoid. This system is controlled by the PGM-FI's ECU, and under certain driving conditions, it will lock the turbine to the impeller to improve fuel consumption. If you think there's a fault there, check it out using either FastCheck or Cobest. Now, one very important point. There's a throttle stop screw just here. It's factory set, and under no circumstances should it be adjusted. You also remember the throttle damper, which we talked about earlier. That has a check valve here, and it's color-coded. Green for automatic, black for manual. If you need to replace that, then make sure you replace it with the right one. So that's it. We've been through the system. We've seen how it operates. PGM-FI is a highly sophisticated, advanced fuel injection system. Sophisticated because its components are electronically controlled for precision and accuracy. Advanced because this electronic control unit incorporates new levels of technology. An ECU that monitors the engine all the time, keeping it in perfect tune. An ECU that can even identify faults in its own system. The PGM-FI system calculates the position of each piston in each cylinder at any given time during the engine's cycle. And it always knows both the speed and condition of the engine. But as well as this, it controls the air intake system, the fuel system, and ignition advance. All this means that the PGM-FI's ECU can compensate for even the most minute changes in driving conditions. So, the Rover 800 always performs smoothly and efficiently. PGM-FI and the Rover 800, a winning combination.